This video will go over sections 4.3 and 4.4 of chapter 4. So section 4.3 is on exceptions to the octet rule. So most of the common elements generally follow the octet rule, which means they all try to get an octet of valence electrons, which means 8 valence electrons around them. And for this, they bind by sharing electrons or transferring electrons. Hydrogen is a notable exception because it needs only 2 electrons when it's binding. It likes to be like helium that has a total of 2 electrons. There are other exceptions, and for example, elements in group 3A do not have enough valence electrons to form an octet in a neutral molecule. For example, BF3, boron fluoride, is made of boron and 3 fluorine. Boron is in the center. And boron in this Lewis structure, you can see that it makes only 3 single bonds and it has no lone pair. So boron in this structure has only 6 electrons around it. And it is a stable structure for boron. So that's an exception. Boron in this case doesn't follow the octet rule. But when I ask you to do a Lewis structure, I will ask you that you always follow the octet rule, except for hydrogen, of course. Other exceptions, happen for the elements in the third row because they have empty d orbitals available to accept electrons. So elements in the third row, third period, they have their third shell being filled. And so, because we are talking about nonmetals here, their 3s orbitals are full, and then the 3p orbitals are being filled. And the 3d orbitals that is higher in energy is staying available in the third shell. And so that's why these elements have d orbitals available to accept electrons, and often they actually collect electrons there. And elements like phosphorus and sulfur may have more than 8 electrons around them. So in the example on the left, we have phosphoric acid, and it tends to have 10 electrons around the P. Earlier we did the structure of phosphoric acid where we had only single bonds around P, but sometimes the oxygen that doesn't have a nitrogen sometimes makes a double bond with P, and then P has 10 electrons around it instead of 8. And it's a stable configuration for phosphoric acid. It also happens for sulfuric acid, H2SO4, where the oxygens are sharing lone pairs with the sulfur, and the sulfur ends up with 12 electrons around it instead of 8. So these are exceptions, but I don't ask you to do structures with exceptions. I always want you to follow the octet rule. So section 4.4, Lewis structures for polyatomic ions. So you remember when we introduced polyatomic ions, we said polyatomic ions are ions overall, but they are made of several non-metals bonded together by covalent bonds. And so then you can do Lewis structures for ionic polyatomic ions. The difference will be that you will need to take into account the charge they have, and you will have to add 1 electron for each negative charge. And if there is 2 negative charges, you add 2 electrons. 3 negative charges, you add 3 electrons. If your polyatomic ion is positive, you will subtract an electron for each positive charge. So that would apply for ammonium, for example, NH4+, you would remove an electron to the total to take into account the positive charge. So here we have an example. It's the cyanide polyatomic ion, Cn-1. So it's made of just carbon and nitrogen. Let's count the total number of valence electrons. Carbon, being in group 4A, brings 4 electrons. Nitrogen, being in group 5A, brings 5 electrons. And then because the polyatomic ion has 1 negative charge, you will add an electron to the total. So 4 from carbon plus 5 from nitrogen plus 1 for the negative charge. It's a total of 10 electrons from the cyanide ion. So next you would do place a single bond between the carbon and the nitrogen. That's using 2 electrons. You still have 8 electrons to distribute. So you will do the octet for nitrogen first and distribute 6 electrons around nitrogen as lone pairs, because those 6 electrons plus the single bond, that will be 8 electrons around nitrogen. So that's using 6 more electrons. So we have used 8 electrons at that point. So the 2 electrons left, you will give them to carbon. However, we have used all the valence electrons. Right now we have 10 electrons in the structure, and carbon doesn't have an octet. Nitrogen has its octet, but not carbon. So nitrogen will have to share, and sharing only 1 lone pair will not be enough. It will have to share 2 lone pairs with carbon. By doing this, you get a triple bond between carbon and nitrogen, and they each have a lone pair. And so if you count, the carbon has 8 electrons around it, 6 coming from the triple bond plus 2 from the lone pair, and same thing for nitrogen. And if we count the total number of valence electrons, we have 6 from the triple bond plus 2 from the lone pair on carbon. That's 8, plus 2 more from the lone pair from nitrogen. That's 10. So we have a total of 10 valence electrons. Another thing that is different with the Lewis structures for polyatomic ions is that you need to use brackets and write the charge in the upper right corner of the brackets to indicate that's an ion. So here we have brackets and then a negative sign in the upper right corner for the cyanide ion. And that's the correct structure for Cn-1. So resonance structures. Resonance structures are 2 Lewis structures having the same arrangements of atoms, but different distribution of electrons for the same molecule. So, for example, you can try to do the Lewis structure for HCO3-1. So, to do this, you would place the carbon in the center, surround it with 3 oxygens, and bind the hydrogen to 1 of the oxygen. And then count the total number of valence electrons. You should get 24 valence electrons. Place the single bonds, deduct the number from the total number of valence electrons, and then distribute the lone pairs. And you will find that carbon is not having an octet, and one of the oxygens will have to share. And so these are 2 of the structures you can get, because either the top oxygen shares with the carbon, and then you have a double bond, going up there, or it's the carbon on the right the oxygen on the right of carbon that can share a lone pair, and then the double bond would be to the right of carbon. Notice how the oxygen that is bonded to hydrogen cannot make a double bond with carbon because it already has 2 single bonds, and oxygen will not make 3 bonds. So that oxygen with the hydrogen cannot make a double bond. So you have two possibilities for the Lewis structure of HCO3 -1, and they are shown here, A and B. Notice how we have brackets around those two structures with the negative sign shown in the upper right corner to show that it's an ion. And so what happens is that the true structure is an hybrid of these two resonance structures. Both structures happen, and the true structure is an hybrid, which means it flips between the two constantly. And instead of having a single bond or a double bond with those two oxygens, it's like you have a bond and a half with the oxygen to the right and a bond and a half with the oxygen above carbon. And so the reason why molecules do flip between resonance structures, it's because resonance stabilizes the molecules. So we will do a Lewis structure with resonance structures for ozone. Let's talk about ozone first. So ozone is formed in the upper atmosphere by the reaction of oxygen and the oxygen atoms. So oxygen is a diatomic molecule made of two oxygen, and sometimes it reacts with oxygen atoms and make O3. Ozone is O3. And so ozone is in the upper atmosphere, and it's a protective layer. It's naturally protecting us against destructive ultraviolet radiations. So it acts as a shield which protects the Earth's surface from destructive UV radiations. So we need to have a good layer of ozone in the upper atmosphere. So let's do two resonance structures for ozone, whose formula is O3. So the first step is to count the number of valence electrons you have to distribute. So we have 3 oxygens. Oxygen is in group 6A, so they each bring 6 valence electrons times 3. It's 18 electrons for that structure. You will place each oxygen in a line, the 3 oxygen in a line, and then you can start drawing the single bonds between the oxygens. Subtract the electrons you have used from the total. So it's going to be 18 minus 4 electrons from those 2 single bonds. And we have 14 electrons left. Next, you want to distribute the lone pairs on the outside atoms, so the 2 oxygens on the periphery. They each have 2 electrons from the single bond, so you need to give them 3 lone pairs, 6 electrons more to get an octet. So you will distribute 3 lone pairs on those 2 outside oxygens, and that uses 12 electrons. So 14 electrons minus 12 from those lone pairs is 2 electrons left. And so those 2 electrons will go to the oxygen in the center because it doesn't have an octet yet. So you give these 2 electrons to the central oxygen, and that uses all the electrons. There is no electrons available anymore. And so the 2 outside oxygens have their octet, but not the central oxygen. And you cannot bring any more electrons. So one of the oxygen from the outside will have to share a lone pair. And let's say, for example, that the left oxygen will share its lone pair with the central atom. And then you will get the structure that you see just below, with a double bond between the left oxygen and the central oxygen. And it's still a single bond with the oxygen to the right. However, you could have decided that it's the oxygen to the right that would share. And in this case, you would obtain the structure that you see on the right, where the double bond is between the central oxygen and the oxygen to the right. So both structures are correct, and it actually flips between the two, and the bonds are constantly changing from one side to the other. The double bonds sometimes is on the left, then the next time it's on the right, and they keep moving between the two. And so really what you see when you look at oxygen, if you analyze it, it looks like a bond and a half on the left and a bond and a half on the right. And that's the hybrid between these two resonance structures for ozone.